Hi students, we're going to try and make this a real quick run through of what you need to know about sound and harmonics. First of all, when you've got sound, especially when you've got musical sound, that is caused by something vibrating with a standing wave. So it hits a certain frequency where you get those waves that seem like they're staying in the same place with the nodes and the antinodes. And that can actually happen a couple different ways. One way is if you have an instrument that has strings, like this guitar here. Wow, that was loud. Or if you have an instrument that plays with a column, an open pipe of air, and the air inside the pipe vibrates. Like that flute right there. Now, in both cases, what's happening there is you're getting standing waves. Now, if you remember from the FET lab that we did with the wave on a string, you could have standing waves where you've got the string attached at both ends, and that's what happens with the guitar. And so on a guitar string, what happens is you get a standing wave. Now, the lowest standing wave you can get is something called the fundamental frequency, okay? And that's when you have a standing wave with just one antinode, like that right there. It is possible to get other frequencies. Let me see if I can undo enough to show you. Like if I've got a frequency that's higher, I can sometimes get a standing wave. No, not you. I can get a standing wave that will give me two antinodes like that. Okay? And there, F would equal 2. Actually, F would not equal 2, I'm sorry. That would be what's called the second harmonic, okay? And we'll talk about the variable that goes with that here in just a minute. But I want to come back to the idea of that fundamental frequency real quick. So let me get it back up here. So I've got basically not even an entire wave, because if you remember, an entire wave has one complete oscillation like that. So what I'm really looking at right here is half a wave, like this half right here. In an open pipe like we have with the flute, what we have instead of having a standing wave with a node at either end, it's more like this gets split in half, and so we have a standing wave that looks more like this, with the oscillation going like that, where the node is actually in the center of the pipe instead of on the ends. Okay? That's sort of similar to saying that it's just this portion of the wave right here. But in either case, if we're doing calculations involving that, then what we're going to do is we're going to use a certain set of equations. So I'm going to scoot this whole thing down here and pop up this other window if it won't close things. Okay, good. And so what we're going to do is we're going to use the equations that are on the top half of that orange formula sheet that I gave to you. Specifically, the one right here, that's f of n equals nv over 2L. Now I want to explain what that means real quick. Okay? What that means is that the frequency for a certain harmonic n is going to be equal to the number of that harmonic times the speed of the wave, or the velocity, and if it's air, that's the speed of sound in air. If that's a string, that would be the speed of the wave on the string, divided by 2 times L. Now L is the length of the string, or the length of the pipe. So this right here would be L, or this right here would be L. Now the reason why it's 2L, remember, is that this wave, this standing wave at the lowest fundamental frequency, is only half of a wave. So to get an entire wavelength, you have to multiply that length times 2. Now things are a little bit different when you look at sound made on something with an with a closed pipe, like this clarinet down here. Oh, and he's going to be loud. So pretty. Now in this case, the pipe is actually sealed at one end, because down at this end of the pipe you got your mouth, right? You got your lips blowing into the thing. And so what we look at there is we look at a column where one end is sealed off. Now this would be very similar to that part of the FET lab where you had the string that was free at one end. And so you could only get, instead of whole waves or half waves, you could get multiples of 1/4 of a wave. So a standing wave on this one would look something kind of like this, with the oscillation going down here. So whereas the ones up above, you're talking about an entire wave, with these down here, what you're looking at is more like 1/4 of a wave, and specifically like this quarter would be this piece right here. Okay, and it would oscillate back and forth. And so the math for looking at sounds and harmonics with the pipe that's closed at one end is going to be very, very similar to the one where it's open, or the string, except that your formula is going to be, let's do a different color here for these, it's going to be f of a certain harmonic, first or second or third or whatever, equals the number of your harmonic times velocity, but this time it's divided by 4L, because again, we're just dealing with 1/4 of a wave as your lowest possible frequency that's going to make sound. Now if you look at, go back to that again, if you look at this formula chart that I made for you, what I did, and the reason why it looks like there's so many formulas there, is that I went ahead and I algebraed out everything else that you might need. So that's if you're trying to find the frequency. This is if you're trying to find the number of the harmonic, the length of your string or pipe, or the speed of that wave. And the same thing down here for the ones with closed pipe. Now, I almost forgot to mention, on the closed pipe ones, because you're dealing with fourths, in order to get a standing wave, your frequency or your harmonic is going to have to be odd numbers. Okay, so this n right here can only be odd numbers like 1 or 3 or 5, etc. Kind of like how only odd number multiples of that base frequency in the FET lab would give you standing waves. So take a look at the problems that are on that paper. Big things to keep an eye out on those is look out for things like unit conversions, because they do have a few of those. You need to be sure that your length is in meters. Okay? Meters. And so if they give it to you in centimeters, remember that 1 meter is equal to 100 centimeters. And if they give it to you in millimeters, remember 1 meter is equal to 1,000, ooh, this is a bad stylus, millimeters. So I hope that was of some help, and I wish you all the best of luck. And if I don't see you again before then, enjoy your spring break. See ya.